For today's class, we'll be looking into electrical instruments from galvanometer down to meter bridge. Galvanometer is also known as milliammeter. To understand the working principle of galvanometer, we have to first get to electromagnetic field. So, but galvanometer is represented with what? G. And it has two terminals. And it has internal resistance, small r. And for every galvanometer, they have what we call the full scale deflection. Full scale deflection current, meaning the maximum current galvanometer can take in. So what is galvanometer? Galvanometer is used to detect or measure small amount of current or potential difference. So if you want to detect PD across a particular material or a conductor, or you want to measure the current and it's a very small value, that's why you use galvanometer, and that's why it's called milliammeter. So ammeter is used to measure current, while voltmeter is used to measure potential difference. Galvanometer can be used to detect both I and V if they have small value. So this is what we are going to talk about, basically about galvanometer. Now, this galvanometer can be adapted or can be converted to ammeter. So galvanometer is the baseline of both ammeter and voltmeter. So, and like I said, to understand its working principle, you have to understand electromagnetic field. So that's not for today. So now let's now see how can we convert galvanometer to ammeter. To convert galvanometer to ammeter, we'll connect to the galvanometer in series, what we call in parallel. Galvanometer can be converted to ammeter by connecting a shunt in parallel to the galvanometer. What is shunt? So shunt is a resistor of low resistance. And why it's connected in parallel, you understand that now. Check this diagram. Now this is our galvanometer. It can take maximum value of Ig. Ig is the full scale deflection current. R is the internal resistance of the galvanometer. Now suppose we have a large amount of current coming in from a source, big I. Let's say the full scale deflection current of this galvanometer is 1 amperes. And what is coming here is 10 amperes. When this 10 amperes gets to the galvanometer, it will destroy it. So we have to divert it away. So that is why we pick 2 points here, nodes. Then in parallel to this, we are going to put shunt here. So let's call it RS, the shunt resistance. The shunt must have a low resistance. Why? If the resistance of the shunt is high, when the current gets here, current tends to flow to where it has lower resistance. The galvanometer has low resistance, low internal resistance. So if this one has high value, most of the current will go here and the galvanometer will still be destroyed. But if this shunt has a resistance lower than that of the galvanometer, what happens? So the remaining part of the current will come here. So go here with the full scale electrical current, which is Ig, and the remaining will come here. So what is coming in is big I. From this big I, Ig will enter here. The remaining part is going to be I minus Ig. We are stylishly applying Kirchhoff current law. Current that enters a node is what leaves the node. Now, if you now observe, these two are now in what? Parallel. So since they are in parallel, it means the voltage across the galvanometer equals to the voltage across the what? Shunt. Since they are in parallel. So they will have same what? Potential difference. So what is V? IR. So what is I in this case? For this shunt, current, this one is for this galvanometer. The current is taken is Ig. So that's Ig, Rg. Why for the shunt, what is coming here? This is current flowing here. That's I minus Ig, Rs. In case you are to look for the shunt resistance, so in this case, if you make Rs the subject, it means the shunt resistance equals to, we divide both by I minus Ig. So we have Ig, Rg divided by I minus Ig. So we can write it this way. So that is the shunt resistance. And that's all. So let's ask, A galvanometer can be converted to ammeter by connecting a shunt in parallel. You can call it gasp or gasp. So here Ig, let's say what each letter represents. What is Ig? The full scale deflection current of the galvanometer. What is R? The internal resistance of the galvanometer. This I is the current to be measured, while this Rs is the shunt resistance. So galvanometer, ammeter. Next is voltmeter. Conversion of galvanometer to voltmeter now. How can we make galvanometer to measure large voltage? Now suppose this is the galvanometer with internal resistance R. Now if you want to measure IPD, high voltage, in this case, to convert the galvanometer to a voltmeter, we need to fix a multiplier in series, GBMS. To convert galvanometer to what? Voltmeter, a multiplier is needed to be in series with it. How? So when you say series, it means for the multiplier, we are going to fix it here. So let it be Rm. I use small Rm because it has small resistance. I use big Rm because it has what? Large resistance. So multiplier is a resistor of high resistance, and it is connected in parallel with the galvanometer. Why? Because let's suppose we want to measure voltage across a body. Let's suppose this is a particular conductor. I want to measure the PD across it. So we are going to take 2 points here and we put the voltmeter here to measure what? The PD. So the two terminals of the galvanometer will be connected, in this case, the galvanometer, between the what? The 2 points on the extreme point of the conductor. Now, if the voltage is too high, this galvanometer what will be destroyed. So that voltage needs to be what? Divided. We call it the voltage divider rule. We need to divide the voltage. So some will go to the multiplier and some will go to the galvanometer. And we want higher one, we want bigger voltage to get to what? Multiplier. And the more resistance of a resistor, the more PD across it. So now let's fix here. So let's say this is the voltage which we want to measure. Source of PD, let's call it V. So what happened here is they are in series. So the current that will pass through the galvanometer, the full scale deflection current, Ig, is the same current that will pass through the multiplier also. Since they are in series, it means total voltage will be the voltage across the galvanometer. So there will be a voltage across the galvanometer, call it Vg, and across the multiplier, call it Vn. So total voltage V, in this case, V equals to Vg plus Vn. Total voltage V was VIR. So Vg was Ig, then R. Internal resistance of the galvanometer plus Vn, the current is still Ig for it too. Ig, then Rn. Suppose our aim is to get Rn, from here it means Ig Rn, we take something to the other side, equals to V minus Igr. So to get Rn, you can double step by what? Ig. So I'll divide this by Ig, this over Ig. So from here, the multiplier resistance Rm becomes V minus IR over what? I. So we can leave it this way, or we can split the denominator. If we split, we are going to get our Rm here to be equal to V over Ig minus what? Igr over Ig. This cancels this. So therefore, it means the multiplier resistance equals to V over Ig minus R. So it means the multiplier resistance equals to the voltage we measured divided by the full scale deflection current, then we must remove it from what? The resistance of the galvanometer. Let me write as Rg also in order not to create confusion. So this is what? Internal resistance of the galvanometer, Rg. Rg, okay, I use Rg here. Rg. Internal resistance of the galvanometer. So that is about ammeter and voltmeter. Before we move to the next three, potentiometer, Wheatstone bridge, and meter bridge, let's go over ammeter. versus voltmeter. So first, for ammeter, it is used to measure current. Voltmeter is used to measure PD. Next, ammeter, this whole arrangement is an ammeter already. So if you combine this RG and RS, this total resistance of this in parallel. If you combine this, you get even a smaller value. So for ammeter, it has a low resistance. So it is a low resistance instrument. So it has low resistance. So total resistance for ammeter is low. For voltmeter, Rm is large and they are in series, so it will add up. So it means voltmeter is high resistance what? Instrument. Now, if you want to use ammeter to measure current across a particular what? At a particular point, ammeter is usually connected in series, while voltmeter is connected in parallel. Please don't confuse shunt. You know, shunt here to the galvanometer is in parallel. But if you want to use this whole combination, everything here like this, we can use the symbol to represent it, ammeter, with two terminals. Everything like this is a voltmeter with two terminals. So suppose I have a resistor. Let me just draw a circuit here. Suppose this is a circuit. And we have a source of PD here, and the key is closed. Then here we have a load. So definitely there is going to be a voltage across this. To measure the voltage across this resistor, so we are going to bring this voltmeter, this terminal here, this other terminal here. Then here we have the voltmeter V. So meaning the voltmeter itself is connected in parallel with that particular device, with the load. Voltmeter is in parallel. But inside the voltmeter, we have a multiplier in series with the what? Galvanometer inside it. But the whole configuration itself is in what? Parallel. Now to now measure the current across this resistor. If you want to measure the current across the resistor first, you have to move the voltmeter first. Because the voltmeter will also have its own resistance, so it will affect this. So we are going to place the ammeter in series. Meaning one terminal of the ammeter towards to the resistor, and the second terminal will be connected to the cell. So one to resistor, one to the cell. So for the resistance, there is one other terminal to the other part of the cell. So that's how it is. So ammeter is in series with the resistor, whose current we want to measure. Voltmeter is what? Is in parallel. Or let's note that. Now another question you may be asked. Why is voltmeter connected in parallel to the load, and why is ammeter to the connected to the parallel in series? First, if you want to measure the current, for example, if you now place the ammeter here, so current coming from the cell, when the current gets here, suppose what we have here is ammeter, it will split into two, some part will go up, some part will go down. Now ammeter has a low resistance. Because it has low resistance, more current will go. Current flows to the region with lower resistance. More current will flow here, and less current will enter through the resistor itself. So, because the ammeter itself will take up current, so what it's going to measure will be incorrect value. But for voltmeter, if voltmeter is in series also, if voltmeter is in series, most of the PD will be shifted to the voltmeter. Only small will be shifted to the body, to the load, because the voltmeter has a large PD. It has a large resistance. And the more resistance, the more PD is going to take. So the device itself will have what? Low PD. So that is why voltmeter is connected in parallel simply because it has high resistance. And ammeter is in series because it has what? Low resistance. So it's not resisting the flow of current coming. Please don't mistake the internal parallel arrangement of ammeter to how it is fixed in a circuit. In a circuit, ammeter is in series with that load. But inside ammeter itself, if you have to bring out this ammeter, I will open the inside, the schematic will be this. Inside you have the shunt in parallel with what? But this time around we're not talking about this series, we're not talking about what is inside. We are talking about how it's placed in the circuit. So on the board we have three major differences between what ammeter and voltmeter. One is used to measure current, other voltage. One is a low resistance device. The other one is what high resistance. Ammeter is connected in series and voltmeter is connected in parallel. Now the next, let's move to potentiometer. We have a small problem here because this voltmeter, they also have their own internal resistance. No matter, they have their internal resistance, and is also going to drive current from the circuit. So most times when we use voltmeter directly, our answer is not usually accurate. So there will be some loss in what? In PD. So in order to deal with this error, we have potentiometer. So majorly to compare the PD, potential difference across two cells. Let's suppose have a cell whose PD is known, and we have another cell whose PD we don't know. So all we use is potentiometer. So this one is also a kind of what? Voltmeter. Therefore, Wheatstone bridge and meter bridge, they are used mainly for resistance, to compare resistance of what? Of two conductors. So potentiometer is a device we use to measure PD. Yes. So we commonly use it to compare PD or the EMF of cells. Although they can also use to compare the resistance of what? Two conductors. Suppose this is a plank. So for a potentiometer, mainly we have a conductor of uniform cross-sectional area, and then it's going to be placed here. So this is usually a meter rule, which is 100 centimeter long, or let's say 1 meter. So on it, let's put a conductor, let's say copper wire. So on it we have a wire AB, length AB, and AB is 100 centimeter, like I've said. Then across AB, first we want to explain the working principle, then we'll now simplify it for example purpose. So across AB here, we fix an accumulator, meaning a cell, secondary cell, and a rheostat, so that we can do some adjustments, mainly to maintain a constant flow of current between AB. Now let's draw an accumulator there. So what we have here is an accumulator, a cell of, let's say the EMF of this cell is 5 volts. It means from A to B is 5 volts. So at this point it's going to be 0, and it will be increasing from 0 to 2 to 3, 4 to 4 until you get to 5 volts. Then here we can have a rheostat. So rheostat is a variable resistor. So it's a resistor whose value can be changed. So if we have no rheostat there, then the PD across AB is the PD across this what? Accumulator itself. Let's call the PD the EMF E. So if we increase the value of this rheostat, this PD will also what? Will change accordingly. But for a particular value of this, a particular current will flow through this accumulator. Then we can also have a key here, so that when no reading is taken, we can open it. So you can either close or open the circuit. Then lastly, we have a galvanometer, a center zero galvanometer. From this, we can fix the galvanometer. Let me use, okay. So let's represent the galvanometer. So this galvanometer, we have a pointer here, or we call it jockey. It's a conductor. So if you place the jockey at a particular point, maybe at the center here, this galvanometer will deflect, showing there is a PD across. So put this jockey here. But galvanometer can only take little amount of PD or current. So we have to put a protective resistor here, so that the galvanometer will not be destroyed. So this one is to protect the galvanometer. And the essence of this one is for us to what? To detect how the PD changes from A to B. If I point the jockey here, it will show a particular value. As you go, it will show us different values. Now, this wire has its own resistance. So the length of the wire is 100 centimeter. So if you move from 0 to 1 centimeter to 2 centimeter, as the length is increasing, what happens? The resistance of the wire tool is increasing. Why? Because resistance varies proportion directly with the length of the conductor. It varies. Now the current passing through this conductor is what? Is constant. Because we can consider this as we are having 100 resistors, each fixed at 1 centimeter interval. So as they are moving this way, what happens? The resistance keep on increasing. And as the resistance is increasing, what happens? The PD also increases per unit length. It's increased by unit length. You know, I said it. For resistor with higher value of resistance, resistor with higher resistance will drive in more voltage. For example, V is IR. So since the current is fixed, it means V and R, they are proportional. So as the resistance is increasing, V is increasing. And why is R is increasing? Because L is increasing. As the length increases, R increases. As R increases, V increases. So V increases from what? From a certain value to what? To the maximum value. So this jockey can be placed any point between A and B. If it's placed at, let's say, points, let's call it one point Q, for example, or point P, anyhow. So it means the voltage between A and Q will be increasing with the length. The longer the length, the more the voltage between A and Q. So if this jockey is here, AQ is small, AQ is getting bigger, bigger, bigger. So first is to understand this schematic. Then next, let's now apply it. What is it meant for? It is used to compare the EMF of two cells, one of known EMF, the other with unknown EMF. Okay, now that you understand this, now let's now draw another diagram. Okay, the upper is the same. This time around, like I said, it is used to compare the EMF of two cells. So let's suppose we have another cell here whose EMF we want to determine. Let me call this one E1. Same thing, we connect to a galvanometer, then we have the jockey. So what are we going to what we are going to do now is, so here let's suppose we have a cell of known EMF here. That's what you have here. Now across this cell, it has its own EMF. But if there is no connection, nothing will happen. This galvanometer will not show any deflection. So if this jockey is placed at this point, it will deflect. You keep tapping randomly. When you tap at a point, let's say you tap at this point, and after tapping here, the value reduces. You keep tapping backward until you tap at a point, let's call this point P, such a way that this galvanometer shows no deflection. So anywhere this jockey is, and it shows no deflection, that is what we call the what? The null point. Or you can call it the node. At the node. So at this particular point, at that null point, it means the PD across this cell, E1, equals to the PD from A to P. So what this Arabic is 5 volts. And this one here is 2 volts. This cell is 2 volts, suppose. It means this particular point is the point that this cell, this AP is 2 volts. So you call it what? The null point. It's called null point, NULL, because there is no deflection. The point where the galvanometer shows no deflection. So we can call this point AP, let's call it L1. Let AP be equals to L1. And we can measure L1 because this is placed on the meter row. This blue blank is assumed to be a meter row, 100 centimeter long. So what are we going to do next? We are going to remove this battery E1. They will place another battery there of different PD, E2. So let's suppose, I don't want to draw another diagram. So let's remove this battery, E2. Let's remove E1 and put another battery, E2. Whose EMF we don't know. So we'll take this jockey away from here. For this E2, this P point is not going to be the null point. Why? Because they are different PD. So if the PD of E2 is small, then it means this jockey has to move to a point, further. So same thing, keep tapping until, let's suppose, when this jockey was brought to this point, Q, it stopped what? Deflecting, meaning no current is here. This is null point, or we can call it the node. So at that point, we can measure from A to Q as our L2. So AQ is our L2. Now from this relation, from here, the voltage and the length also have indirect relationship. So E1 is proportional to the length. Same thing goes for E2. E is proportional to length, to L rather. So for you can say E equals to KL. So this for E1, this for L1, which is AP in this case. So if you do for E2 also, E1 was the initial cell. For the second cell, we have E2. E2 also gets KL2. And what's L2? AQ. So what we just need the voltmeter to do is to know the value of L1 and L2. So what as we don't know E1, we don't know E2. So we want to use the potentiometer to calculate what? L1, the first non-diffraction point for the first cell. Then L2, the second non-diffraction point for L2. So from here, if you do mathematics and we divide both sides, from here you can say E1 over E2 equals to what? KL1 over KL2, and K cancel each other. So at the end, it implies that what? E1 over E2 equals to L1 over what? L2. This is for a potentiometer. So if you have two cells, we can always calculate L1 and L2. But to know E1, you have to know E2. To know E2, you need to know what? E1. So those two cells we tested, we use E1 first. If E1 is known, we calculate L1 for E1, then L2 for E2, then calculate it from here. So you'll be given a question like this. The length of the balance length is also for a particular cell of 2 volts. What will be the area of another cell whose balance point is, let's say, 20 centimeters? So they will give you L1, L2. They will give you either E1 to get E2 or E2 to get E1. I will have skipped all this step and just move directly here and give you this formula. It's very easy to work with. Question on potentiometer in JAM is very, very easy. Even in WAEC, although there are some questions that you need to understand the basis, because you have to understand the basis. So that is why I explained this. So that is all for potentiometer. But before that, potentiometer, like I said earlier, is better than voltmeter. Why? Because while using potentiometer, this null point shows that no current is flowing. So it means it is used to measure the EMF of a cell when it is driving no current. So when it's driving no current, it means the internal resistance of the cell has no what? Effect. But for voltmeter to measure, voltmeter has internal resistance, so it's going to give us less accurate value. So potentiometer is better in measuring what? PD across a conductor compared to what? A voltmeter, because it is used to measure the PD when it's driving no current. So if you use this method, it gives us the actual value, unlike the voltmeter. So you have to understand the diagram very well for other purpose. So the first cell is E1, and that E1 is the one that gives us this P. So let me write P beside it. This E2 is one whose deflection gives us Q. Let me write Q beside it also. Q. So AP is the length for E1. After I remove E1 and put it there, AQ is the length for what? And note, this conductor itself has a total resistance. Let's suppose the resistance of this wire is 100 ohms. Let's suppose the resistance is 100 ohms. It means per centimeter, the resistance is what? 1 ohm per centimeter, because everything is 100 centimeter. Next is Wheatstone bridge to compare resistance of resistors. So we have 4 resistors. Let me draw it. For this particular arrangement, we have to show the source of the energy, which is the cell. So suppose this is a cell here. The cell is across this way. Let's call it PD V. So this can be an accumulator. So it's going to drive current. So let's say you drive current I from the source. When the current gets here, this is a node. So some will go here and some will come here. Later on I will go up here is to the I1. The one down here is I2. Let's label all the resistors as R1, R2, R3, R4. Now when this current gets here, the same current that flows here will pass through this R1. So the current that passes through R1 is also what? I1. So here we have I1. This R2 passes through R4. This is not a node. So this same I2 passes through R3. So the current through R3 is also what? I2. This is so when this I1 and I2 meet, they reconnect and the flow continue this way. But the thing is, we cannot be certain if this arrangement will be balanced this way. So for us to be certain that this will be balanced, so between this point and this point, let's suppose we have a galvanometer. So if this point and this point is in contact, and this galvanometer shows no deflection, and it shows no deflection, so it means these 2 points are like, it's like a single point, like a node. So in that case, it means this resistor and this resistor, they will be at the same potential. It means R1, R3 will be at the same potential, R2, R4 will also be at the same potential. So when you put this galvanometer here and we connect it, and it shows no deflection, so it means R1, R3 they are in the same potential. So it means the PD across R1 equals the PD across R3. And what's the PD here? I1, R1. For this one is I2, R3. So same thing goes for this one. The PD across R2 and R4 will be the same thing. So PD across R2 and PD across R4 will be the same thing. For R2 we have what? I1, R2, I1, R2. And for this one we have what? I2, R4 for this. So what can we do? Let's divide this one. Let's divide this one by this. So what we have here is I1, R1 equals to I2, R3. Then for this one we have what? I1, R2, I2, R4. Now from here, what happens? This cancels this cancels this. So at the end of the day, we'll be having R1 over R2 equals R3 over R4. Now what's the point? If we have 3 resistors and they are arranged this way, and here shows null deflection, so it means if we divide the resistance of the resistor up R over R2, we get the same thing as dividing what? R3 to R4. So if we have 3 resistors of known values, suppose R2, R4, R3 are known, and I want to get R1, that is when you use what? Wheatstone bridge. So this is the arrangement for Wheatstone bridge. Out of these 4 resistors, 3 of them will be known, 1 is going to be unknown. That is all for Wheatstone bridge. And lastly, we move to meter bridge. For meter bridge, it's like the combination of potentiometer and what? Wheatstone bridge. It's like a practical arrangement of a Wheatstone bridge. But this time around, we are not going to use 3 resistors. So similar to what we have here. So we have a conductor, and we can label this place AB. Then we get 2 conductors, maybe copper strips. So to form like L shape here, L shape here. Then one in between with a space. So what we have here is, it can be copper or brass. Then we have another strip here. So what are we going to do next? This is our R1, we can bring it here. This R1. Then this R2, we can bring it here. R2. So what next? We can get a galvanometer. This galvanometer G with the jockey. So this galvanometer is going to be tapped on this metal randomly until it shows no deflection. So suppose we tap it at this point P and it shows no deflection, so this arrangement becomes this arrangement also. How? So this is our R1. AP, what is no resistance? That's our R3. PB, what also has no resistance? That's our R4. So we are going to apply same formula. R1 over R2 equals to R3 over R4. We know that the resistance varies with length, and R equals to KL. From there we can say R1 over, we can replace, okay, R1 over R2 equals to, we can replace R3 with KL. In this case, What's L6 or R3? Let's suppose from here to here is L1 PB, and PB from here to here is L2. So it means this K is what we call resistance per unit length. So this wire has a constant resistance per unit length, but we don't really need it here until maybe if you are given the question. So we can replace R3. I can say R3 equals to that constant K, then L3. But in this case, our L for this R3 is from what? A to P, that's L1. Then our R4 also is also KL. That will be K. What will be L? That will be L2. L2 from here to here. So we can come here and write K L1 over K L2. So the resistance per unit length will cancel each other. So it means R1 over R2 equals to L1 over L2. So for a meter bridge, let's suppose R1 is unknown and R2 is known. We only need to know the value of L1 and L2. We need to know the value of L1 and L2. We know that from A to B is 100 centimeters, so it means L1 plus L2 equals to 100 centimeters. So I can also write this one as R1 over L1 equals to R2 over L2. It also works that way. Yes, you can arrange this mathematically. If you cross multiply, you still get the same thing as what we have there. Then from here it's obvious that L2 is 100 minus L1. So we can say therefore R1 over L1 equals to R2 over 100 minus L1. So we can be told that for a standard resistance that is known R1, we are told to look for R2 and are given the balance point for the first one. So this formula works. So you either combine these two together separately or use it directly. So that's for Wheatstone bridge. But for a potentiometer, although they look alike, for this potentiometer, although we can also put a cell here, but it doesn't matter. This L1 and L2, they don't add up to 100. They do not add up to 100 because we are using two different cells. So, but for meter bridge, it works. Now, if you understand this basis, sometimes you can have a question that they will link potentiometer to a meter bridge. But for this class, we are done with electrical instruments from galvanometer down to meter bridge. What is left is to solve question on electric field 3.